This video is going to be about the conceptual part about the heating curve of water. So there's no quantitative calculations in this example. It's just going to be talking about the changes of energy as the temperature changes. And we do know this is a direct relationship pretty much overall. As the temperature increases, it's because heat has been applied over time. We know that we can have ice colder than 0 degrees Celsius with use of the freezer. And at 0 degrees Celsius, water melts from solid to liquid. Liquid water is from 0 to 100 degrees. I have not drawn this to scale. The heat of vaporization occurs at, or is required at part 4 to raise your liquid water to gaseous water. And then you can superheat steam in section 5, as you saw in the demo in class. So what I'm going to talk through on this sheet is each section of the heating curve. I'm going to talk about how temperature changes in 3 of these sections as you go across them. And remember that temperature is a measurement of average kinetic energy of the particles. We're going to show kinetic energy in our particle models as swooshies. Potential energy, we're going to connect to delta H, the delta H of fusion, the delta H of vaporization, or our phase changes. Potential energy, phase change, plateau, they all start with P and they connect really nicely together. Final thing we're going to do is draw a particle diagram. So I've done all these for you, so you can press pause as you needed to fill this in. But in section number 1 of your heating curve, this is where you have a solid state of matter. The temperature is increasing in my example from -10 to 0 degrees Celsius. As temperature increases, our number of swooshies will increase. If I was drawing this as I did over here, whatever the coldest temperature in your particle diagram is going to start with 1 swooshy. So I drew my solid molecules close together, gave them 1 swooshy each. So in thermochemistry, we're going to draw swooshies even on our solids. In unit 1, we just drew them on gases, but in unit 4 in thermochemistry, we really want to make sure that we're showing that kinetic energy as those particle movement lines, or I call them swooshies. Every time you draw a particle diagram, you need to draw a temperature along with it. I chose -10 degrees Celsius. I could have chose -5 degrees Celsius, but that's my starting point here. It's going to be the coldest temperature out of all the particle diagrams that you see. So it's going to start with 1 swooshie. As I move to the next section, you're going to see that my potential energy that I kind of left out of that brief discussion, because it's constant in section 1, that changes in section 2 because I have a phase change moving into section 2. So section 2, I no longer have increase in kinetic energy, whether I'm at the beginning, the middle, or the end of section 2, melting ice, solid to liquid, my temperature is constant. My kinetic energy would be constant, whether I'm drawing the beginning, middle, or end of this phase change. But what this energy is changing into, should scooch down the rest of this because it looks like I haven't drawn my particle diagram properly. My potential energy is being changed as the phase changes, or these solid particles, they were really close together and now they're going to start being ripped apart. That's the potential energy change. My energy does not change for my kinetic energy. My temperature is going to stay 0 degrees Celsius. So my solid particles and my liquid particles, I'm trying the midsection here, would have 2 swooshies. I've just upped my swooshies from my previous temperature checkpoint. Remember, these are just particle models, so they're just going to be a representation of what's going on at the atomic level. If I was drawing this point right here, I would still draw 2 swooshies, 0 degrees Celsius, but all solid. If I was drawing this point right here, still two swooshies, but I would be drawing all liquids. I chose to draw the midpoint, liquid and solid, these particles all at 0 degrees Celsius represented with two swooshies, two kinetic energy lines. All right, next up, I actually draw my particle diagram at 25 to 75 degrees Celsius. So you'll notice I've got in my green section here, from 0 to 100 degrees, two particle diagrams. And in this section from 0 to 100, again, not drawn to scale, sorry, I have temperature increasing in this section, 0 to 100, kinetic energy is increasing, but there's no phase change. The potential energy is not ripping apart the liquid molecules into gaseous molecules quite yet. So I have 3 swooshies as my next checkpoint. And at a point you draw a lot of swooshies. So if you'd like to just draw 3 swooshies on one of your particles, or if you want to put a number 3 in the middle, that's okay too. Or if you want to draw 4 swooshies, or if you want to write at number 4, if that's easier, because we're going to end up drawing a lot of swooshies and I want you to go swooshy crazy. So if it's easier just to model one, because all these particles are 25 degrees Celsius, they would all be represented with 3. My next kinetic energy change checkpoint that I picked in this example was 75 degrees Celsius. So I'm representing that with 4 kinetic energy swooshies. My next section, think about, oh, I'm going to have a phase change. Is kinetic energy changing or is potential energy changing in section 4? And what's going to change here in section 4, if you were right, my potential energy is changing because I have a phase change. My liquid molecules are being ripped apart at 100 degrees. So liquid particles, gaseous particles, yes, both 100 degrees Celsius. So the liquid particles, I have a 5 by or representing 5 swooshies. All of these particles, doesn't matter if they're liquid or gas, kinetic energy and temperature are constant. So it's going to be 100 degrees Celsius, whether I'm at this point at the beginning of the phase change, the midpoint, which I drew down below, or the end. The only difference is the midpoint's going to have liquid and gas. The beginning would just have liquid, 5 swooshies. The end would have gas, 5 swooshies as well. The final point I chose to draw in terms of particle diagrams happens to be in section 5. In section 5, my kinetic energy is changing again. Potential energy is constant, no phase change. So what's drawn here are 4 gas particles, 6 swooshies represented at 110 degrees Celsius. So there's little 6 in that particle model. So whether you have kinetic energy or potential energy changes depends on which part of the heating curve you're out. Recording here at the end of the day. So there's announcements. What I was saying earlier was that the part of the heating curve depends on what you're changing conceptually going on with the chemistry.